Welcome everyone to the final talk of the StatEase 2025 Online DOE Summit. Thanks for sticking with us for this week of wonderful talks. Our final presenter, eighth, and I don't know of anything else that starts with an E, Eric, is our final presenter for the summit this year, and we are very excited to see how he tackles this multivariate and multi-level challenge. Eric, it's all yours.
Thank you, Rachel. First of all, thanks for joining me. I've got with me a presentation on a multivariate and multi-level challenge from the nuclear sector. So my name is Erik Koppens and I'm employed at Onder Nijwes, which is the Belgian Waste Management Organization. Now, allow me to give us if my presentation will be working. Yes, okay, it's working. So Belgium, I said, indeed, we are so the Belgian Waste Management Organization, Nuclear Waste Management Organization. Obviously, we are situated in Belgium, Europe, and the mission we have, or while we do what we do, is to protect man and environment against the potential risk or harms that radioactive wastes might impose. And that is our mission. And radioactive wastes in Belgium, I've got a picture of them with me. Most of them, they are in a bunker, a big bunker, and filled with these metal drums. In these drums, we find the radioactive waste. Radioactive waste in these drums is always a solid material. Nevertheless, a lot of radioactive waste is liquid when being produced or gaseous. So to get it or to assure that it is a solid material in these drums, we apply some kind of a treatment process, a conditioning process that renders that liquid state into a solid state. And that just makes our life at the end way easier. So to manage them, handle them, and assure there's a safe solution for them in the long term, we need to have them conditioned and need to have those radioactive materials to be solid in those drums. So the content of all those drums is solid, there's no liquid inside. So that is a very important context. Now, the remaining of my presentation is on the context of the problem I have with me, which is on a conditioning process. And then I will try to explain the problem we are facing. Obviously, some design of experiments, because that's why we are here, and then some statistics concluding with an inference. Now, let us bring us to the context. As I stated, this is on a conditioning process. We are facing the conditioning process of an intermediate level waste. So intermediate level means rather high level. You do not want to be close to that material at all. The conditioning process I have with me is one that is currently in development. So we are not up and running yet. We are still in development phase. We are building the infrastructure, but yet we need to have a very good idea about how we're going to condition that waste we're talking about. I will show you in a second before we can actually build the infrastructure, that we will be needing for that conditioning. Right, so this is a photograph of a gate of Belgo Process. That is our industrial subsidiary in Belgium. And somewhere behind this gate in the woods, there's a big reservoir called Reservoir 54013. And that's filled with liquid waste. That highly, or at least intermediate level radioactive waste. So when the conditioning process consists of taking a batch from that waste and then evaporating a lot of the water to get away the nuclides on a smaller volume, to get the waste in a smaller volume. And obviously the extent of that process can be quantified through what we call the concentration factor. That is the extent to which that process is, will it play that process actually. That's important to capture because I will be referring quite often to the concentration factor in the remaining of the presentation. Now we're facing a highly acidic waste. So we're talking about pH 8. And further on in the process, we're going to intermix that with cement. And most of these cements have an alkaline pH, so around 13. You can't just mix that pH 0 with 13, that will have a tremendous violent chemical reaction. So we have to pre-treat this concentrate, we call it. You have to pre-treat it with a base to get the pH to a higher level before we can actually later on mix it with cement. And we do that with a barium hydroxide base in our case. Once the chemical is chosen, once the chemical for the pre-treatment is chosen, the extent again of this process step can be quantified through the pH we eventually attain. And that's so again another thing to remind, because I will again make a lot of references to that. Then we let the thing to rest for a night, and we finally mix it all with cement and other materials in a drum. So these are the drums that will end up in those bunkers. We let it rest and under monitoring to harden out. And once it's all solid and hard, we can remove it and place it in those bunkers for which you have seen that big pile of waste drums. So it will be one more drum amongst these other ones. So this is the process that is the subject of my investigation. And I think it's clear that there are two buttons we can turn to steer this process. We have two buttons under our control, that's the pH and the concentration factor. We can add more or less base to get a particular pH and evaporate more or less water to get a particular concentration factor. But the waste itself, even though it's always from reservoir 54013, it does vary a bit. Each time we take a new batch or a new sample, there's a slight variation on that waste. And also, I've said we're using cement, but the exact cement batch, there's some variation on that batch, and even the supply of cement can be a lot of variation. Obviously, there are other materials, and there might be an error. So we don't have everything under control except for, in some extent, the pH and the concentration factor. So I try to make that distinction clear by these two colors in this graph. Now, the problem we're facing is that the waste package we're producing, the end product, the properties thereof, they are of tremendous importance for the further management of this waste. They are foundational to a safe management. So there are very strict criteria or specifications to which we have to adhere to in order for us to be able to manage them in a safe manner. Now, whilst on the other hand, to foster economic competition, public tendering of materials is highly encouraged, meaning that a priori the exact supply of the materials is unknown and might change quite often. And also the waste itself, as I already indicated, can vary a lot from batch to batch. So the question we have now is, what must these production settings be, concentration factor and pH, to assure that the products, the waste packages are indeed according to specifications? And I will try to answer that by quantifying the combined effects of both the fixed effects and the random effects. I will be doing that by leveraging general least squares, which can be done by in studies 360. And then eventually the outcome, as you will see, will be a set and forget parameters. So I will be able to pinpoint what parameters will lead to waste packages that are according to specifications independently of the exact materials we will be having, and also independently of the exact chemical composition of the waste of this waste, even though it might vary a bit from time to time. So how did we do that? Obviously, a lot of design of experiments was involved, and the main idea is clearly it's a factorial experiment in two continuous factors. So we're talking about concentration factor and pH, but to that I've added a block. So we're facing a blocked experiment, and that I find the clever part actually. Each block is a distinct combination of materials and waste. So a distinct combination of whatever material we might have now or in the future, and whatever waste we might have, as long as it comes from that reservoir 54013. And these are the random effects. So that leaves us to get the design, make the experimental design. After doing some calculations, it became clear for me that I had to end up somewhere in around 20 runs or so. That was what I needed, and there was a budget for also. I wanted to have at least 5 blocks. That seemed to me the minimum to say something meaningful about the potential effects, the random effects that might be that might come from a change in materials. And so I did compare ID and A optimal designs, always adopting the quadratic model with interactions, and I assumed fixed block effects. I've checked leverages, the inflation factors and prediction accuracy, also checked alia structure. And I can't recall exactly, but I think I ended up with the A optimal design, but might as well be the I optimal design. I'm a bit in doubt right now. Nevertheless, what I've done afterwards is I've added more experiments. I added obviously some verification experiments, 6 in my case. 2 of them I've added in blocks that were already in the main design. But the other 4, I've placed them in 2 new blocks. So there are 2 blocks in my design that will not be used for building a model, but only will serve as verification run. And the first run, it is my experience that it's often prone to error, so I replicated that particular run. And that brings us to a total of 27 runs with 7 blocks, so meaning 7 lack of fit degrees of freedom and 4 pure error degrees of freedom. Now, how did we do the sampling? Well, the sampling of the waste 54013, that is not as evident. As I said, it's highly radioactive. You do not want to approach it, but obviously we need to get some samples from there in order to understand what the waste looks like. So that is what we did. We've taken a few samples, 7 small volumes of liquid, not enough to do the experiments with, not at all, but enough to analyze the chemical composition of this waste. Because indeed the goal was not to understand the average composition of the waste, the goal was to understand the distribution of these chemicals. And with that information, we will be able to make surrogates later on in the laboratory. And these surrogates, they have all the chemical elements in them except for the radionuclides. That might feel a bit odd because we are talking about radioactive waste, and yet I will not be using radioactive materials for my surrogate waste. That is because the concentration of the radionuclides in such a waste is multiple orders of magnitude lower than the concentration of the stable nuclide, of the stable elements, meaning that the physical chemical characteristics of these wastes are not predicted or not imposed by the radionuclides, but they are imposed by the stable elements, the classical stable elements we all work with in the laboratory. So data came in on the composition of these 7 wastes. What I've done is I've estimated the distribution of these elements that we find in this waste. I slightly inflated a bit the estimated standard deviation, just to be sure that later on my inference is relatively prudent. Then we have done some pseudo sampling from that inflated estimated distributions. So the computer told us, has given us some we let the computer sample from these distributions. And then we produced, in line with those computer sampling, we produced surrogates to be used in the laboratory. And these random 7 surrogates, they were allocated to these 7 blocks I have. A fair question will be now, is this surrogate waste still a good approximation of the real waste? And that is indeed the question we have to solve. So we've done some testing, A/B testing, in which we had a group surrogate waste and a group real waste. And we've measured some things on these wastes. And what we've done is we have mimicked the actual process on a lab scale. We'll also do that in the following of my presentation. But we've done this here also with the real waste on a very small scale. But the issue is with real waste, you can't approach it. You have to work in a hot cell with tail manipulators. I've got a figure of that in my next slide. But you can't measure anything you want, so you have to make choices. And the things you can measure are very often not really what a waste management organization would be per se interested in. But you have to do something. You have to be assured that the physical or mechanical behavior of what you're making is very close to the of the surrogate material is very close to the real waste. And in the illustration I have with me with those multiple steps, we first have the liquid waste. Then if you add base, we have the sludge. And then if you mix it with cement, we have fresh cement, and afterwards it gets hard. And so we've got 4 stages actually, and what we've done is for each of these 4 stages, we try to find at least 2 responses, one response, 2 if it were possible, that would allow us to discriminate or to compare the behavior of these 2 groups with. So it was again a designed experiment. There were a lot of constraints, obviously, but we've verified power and all, so we're fairly confident that these surrogates we are producing are indeed a close approximation of the real thing. Here, that figure I talked about, that photograph. So these are photographs of the wastes in a hot cell. You can see the tiller manipulators coming in. A true technical challenge to manipulate these things on a small scale. I tried to do that myself, and once just not really to play around with, but to get a feeling. It's not obvious, not at all. So heads off to those colleagues at Belgian Process. That was a tremendous job they've done. Now, let us get back to, oh, my presentation is gone. Sorry.
You never can account for equipment failure, can you?
No, you can't. No. I'm gonna swap this. Right. So, where was I? Fast forward. It's good reminder of what I've said. So I was here, and right,
Yes, this one looks right.
I was talking about sampling. So we had the sampling of the waste. The sampling of the other materials was way more straightforward. We just sampled them from the Belgian market. Well, not Belgian market, we sampled them from the market. We are in Belgium, so we sampled from the Belgian market quite a lot. But next to them, we sampled also from France, Germany, the Netherlands, and UK. And those materials were then located, as I said, allocated, as I said, randomly to these blocks. This eventually is the design or part of the design I came up with. 2 factors, 7 blocks, and the block is a random combination of waste and other materials. So the factors are the blue things I have under control, these things I can tweak in my process, and the combination of waste and other materials are thus the red arrows I do not have under control, except for the error that is obviously always present in each run. So all of that was well, now we have the experimental design. We have the raw materials, we have the surrogate waste, we know what concentrations to use, the concentration factor and pH to use. Let's talk a bit about the responses. What did we actually measure? It must be clear now that we are conducting now experiments on the bench, the classical bench. No radioactive materials are involved anymore, so we can actually approach the material we are making. We will be mimicking the process, the production process on small scale on the bench. And we will be measuring a lot of mechanical properties like flexible strengths in multiple kind of environments. We will be placing these small hardened cement pieces in multiple kinds of environments and observe how their strength evolves next to both flexible and compressive strength. But we will also measure things as thermodynamic properties, for instance, the kinetics of heat development and the total heat that it's going to get developed, because cement does get warm, and that is a very important information for us that will become clear in the following of the presentation. We also check material needs. How much space do we need to get the pH to a particular target value? And all of that was then brought into a lab protocol, which was 13 pages thick explanation to the lab technicians what to do exactly, together with some fill-in response sheets, just to be sure that it was all very well documented and we had all the data in the correct format, etc., to be able to use afterwards. Let's talk about using the data. So experiments are conducted at the process laboratory. They come back and we analyze the data. Let's talk a bit about first pre-analysis. Let's talk about factor adherence. Concentration factor, right? That could be easily tweaked during the experiments because we could simply dissolve more or less chemicals into the surrogate waste to mimic more or less evaporation. But the pH, that was not so easy to be tweaked. The experimentalist had to add base to that concentrate, to that surrogate of concentrate, just to increase the pH to that particular target value. And it turned out that there was quite some scatter. So we do not always get the exact target value we would like to have. Next to that, there was also some overshoot, 0.15 pH units to be exact. So based on this information, we've decided to not use the pH as intended in our analysis, but use the pH, the actual measured pH in our analysis. So we've ignored factor 2 and we've added a new factor, which was the actual pH that was being observed in the experiment. When one changes the factors of an experiment, even the units or their physical meaning or whatever, it's a very good idea to have a step back and verify what the knowledge space now is in that new dimension or in that new factor range, just to be sure that we won't be using any extrapolation, because we really want to avoid that if we want to make meaningful inference. So the blue points on this graph are the actual experiments we've conducted. The check marks are also actual experiments, but these are the ones that will not be used for model building, but will be used for verification purposes. And based on these blue points, we have now redefined the knowledge base, or the experimental space, or whatever you want to call it, as that rectangular. So that was defined prior to the analysis. That was defined in the pre-analysis. So it slightly changed a bit from the initial window we were trying to capture. So it's slightly broader now, and it slightly shifted to a higher pH range. The concentration factor stayed the same because the factor adherence was very easy, but for pH, so that wasn't the case. No, and obviously that one confirmation point is outside the knowledge space. We will be keeping it for verification, but if it's off, it's off. I mean, it's an extrapolation, so we can't expect it to be well predicted by these models we're going to build. And nevertheless, these models might serve a great purpose in a knowledge space itself. So I believe that it's very important to really pinpoint a knowledge base and to avoid making inference or try to make inference for situations that are outside of that knowledge base and really don't do any extrapolation or not too far extrapolation. Now, this graph is a bit deceiving because it might seem that our knowledge space is 2D, while no, in reality it's at least 3D, because the depth of my knowledge space is all the possible combination of materials and waste from that particular reservoir. So I think that's important to understand. The depth are the most of the yellow arrows, except obviously, of course, the experimental error. Now, as I stated initially, now we're into the analysis now. So the design was developed as we were going to analyze this data with fixed block effects. So a fixed but unknown effect that each block introduced to the outcome or to the observation we are measuring. But that's not how we are going to analyze this data. We're going to analyze them as random. I mean, the block, we are going to approach the block effect as random but unknown a priori. So the model changes quite significant. The dummy variables that are related to each block are now changed for one distribution, which is a priori assumed to be normal distributed about 0 with an unknown standard deviation that we are going to estimate. Now, luckily, all experiments that are designed for fixed but unknown blocks, they can be analyzed under the assumption of random and unknown blocks. So that's a good thing. It's a bit suboptimal, but it can be done. That's what we've done. And to be honest, I find it a bit prudent too. So I still think that's quite okay to do so. I mean, designing for fixed block effects while analyzing for random block, I don't see anything against that. Choosing whether one wants to analyze with random effects or block effects is very easy to do in Studies 360. You can just toggle it on or off in the configuration pane, as you can see on my screen over here. Now, let's talk a bit about the modeling, the models I've made. So all of them polynomial. Of course, we checked for transformations, whether they were adequate or not. We've done that through the box-Cox plots. Residuals were inspected for normality, independency, and identicality. And we've done some model selection, mainly through Ikeikis information criterion. And if required, if some of the models were in very close competition, we've done some model averaging through the weights, the Ikeikis information criterion weights. But eventually, we had to confront the build models with the 6 observations, the 6 confirmation experiments. So in practice, we have compared the prediction intervals for those particular treatments with the actual observations at these treatments. And it turned out that all of the models we have built, and we had like over 10, if I recall correctly, we had 15 responses. But all the models we have built were well predicted. Sorry, all the models we've built well predicted the validation points or confirmation experiments, except that one validation point that was in the extrapolation zone. But that's, of course, not very surprising. Now, what have we done with them then? Let's go to the inference. What we've done with them afterwards at this stage is we now have these confirmed models. And recall that the goal was to get the the process settings, concentration, factor, and pH, as such that it just always works. So what we've done is for the whole knowledge space, we've generated predictions of the outcome of the observations. And very often these predictions could be easily compared with the product specifications. There was a one-on-one comparison that was very easy for some of them, but other predictions had to be combined, and they served again as input for another model, often a meta model, and then the outcome of that meta model could be compared with the product specifications. Now let's talk a bit about the meta model, how it looks like. There was a talk on meta models previously, on this summit, and I think it's the same idea. So it's approximation, at least how we have approached it's an approximation of a more complex model. So, for instance, we measured the time it takes for the maximum temperature to occur in these specimens we produced. And we also measured the heat of hydration these specimens develop. Those two things, they serve as they serve as an input to measure the maximum temperature of the waste package. And we knew, at least with models that we've produced, we can predict what the time of maximal temperature is and what the heat of hydration is in function of the concentration factor and the pH, because we have developed polynomial models, the classical ones. So all of that end up in an analytical model together with the environmental temperature that tells us what the maximal temperature of the waste package will be. Now, that's a bit of a complex situation, two polynomial models that will serve as an input for an analytical one, plus the environmental temperature, and then eventually the maximal temperature of the waste package. Now, we have tried to simplify that by computer interrogation. So we try to approximate that ensemble of those three models with polynomial. And the polynomial now has as input concentration factor, pH, and the environmental temperature. And the outcome of that polynomial model is then again the maximum temperature of the waste package. A computer interrogation is a very similar idea as DOE. The only thing is there's no noise. So if you ask a computer to calculate the deterministic thing, you get the exact same outcome. And computer interrogation and the meta models or the development of the meta models, they're often combined with Gaussian processes. And one can also do that in Studies 360. Again, a snapshot of where one can do that. It's again in the configuration pane. Well, we didn't do that. We've used polynomials. Why did we use polynomials? Because the polynomials can be easily plugged in into Studies 360 in the responses. So you can actually ask Studies 360, to calculate an outcome based on certain factors. And again, that is right click on responses, and then you've got this, you can choose what kind of response, what you want to do. You can fill it with random materials, but you can also fill that response with a formula, and that's what we've done. Now, it turns out for all these responses we've predicted, a lot of them. Now, only a few were not always according to specifications, and these few, they are of course critical to quality. And the most important one, let's talk about the most important response that was not always according to specifications. That was the temperature. So sometimes the waste packages, they tend to get kind of warm, and we have to limit that maximal temperature of these waste packages in order to assure ourselves that the phases are being developed or being phase assembly eventually, the material of the waste package is stable over time. So we have to limit the temperature, cannot be too high. Now to answer the question, what concentration factor and pH we must be using to assure that the temperature is never too high, we have tried to answer that through the use of tolerance intervals. We have adopted the 2.5% AQL level, meaning that we were trying to infer for 975 waste packages on 1,000 waste packages. And the confidence level we have adopted was 75%. And then eventually we end up with graphs as such as these, where the yellow zone, it's a bit in function of the environmental temperature. That's because of the meta models we've used. But the yellow zone tells us where the settings of concentration factor and pH must be as such that with at least 75% confidence, 975 on 1,000 color are indeed according to specifications. Or with 75% confidence, at least 975 1000 color are according to specifications. And that will work irrespective of the materials and the waste batch that we will end up with. So that is the end of my presentation. I'm happy to take any questions now or by mail. My mail address is on this slide.
Okay, thank you, Eric. As he said, if you have questions, go ahead and put them in either the chat or the question module. So we've got one question. Why did you use 5 and not any other number of blocks to represent the natural variation?
Yeah, very good question. To model natural variation, I used 5 blocks indeed. More would have been better, but well, I didn't want to explode the number of runs. I mean, to increase it to a too high level. And I felt like 4 was a minimum, right? I at least needed 4. So I just added one more to get to 5. But indeed, more would have been better. And I didn't really have the means um, to do a quantitative analysis or make a quantitative criterion on what would be enough. So it's a very arbitrary choice I've made.
We will go ahead and wrap this up. Thank you, Eric, for concluding the 2025 Online DOE Summit. If you haven't seen them already, the rest of the week's talks are up on our YouTube channel. Feel free to share those around with your colleagues, host viewing parties, anything to get that DOE education out there. We welcome questions both at StatEase and to individual presenters, and we look forward to hearing from you about how you have made the most of your experiments through DOE. Have a wonderful rest of your, at this point, weekend, and we'll see you at the next webinar. Thank you.
Bye bye.